talking about section 2.2, graphs of equations. And really, just to give you some insight into where we're going in pre-calculus, is we're going to spend the next really substantial portion of our course talking about graphs of equations and functions. So we're going to learn how to plot points today, and then as we introduce each sort of family of graphs, we're going to learn about transformations and how we can use a base graph to kind of generate all of the possible other graphs. And so when we graph the solutions to an equation, in the plane, it is called the graph of the equation. So remember, those solutions are the values for which an equation is true. So values for which an equation is true. And so if we take all of those solutions and we plot them on a graph, that result is called the graph of that equation. And so we talked about ordered pairs in the Cartesian plane in our previous video. And so an ordered pair, remember, ordered pairs look like one number then another. We say that it is said to satisfy an equation with two variables, right? So if we only have one variable, we would just need a single value to satisfy that equation. But with two variables, x and y, if when we substitute a for x and b for y, right? Because this a is our x coordinate and b is our y coordinate. The resulting equation is true, right? And so thinking about true, we can say that AB is a solution of that equation. And so let's first just practice checking to see if a given point is a solution to a given equation. So consider this example. 2y equals 3x plus 5. And what we can do here is we really can, I would say generally speaking, it's nice to have one of the variables alone, because then when you plug in, say, your x value, you can just get your y value out, right? And so that's the same as if I go ahead and divide both sides by 2. Remember, that preserves equivalence. That's the same as y equals 3x plus 5 divided by 2. And we'll just go ahead and leave it of that form. So here are a couple examples. So we have points, and then is it a solution? And so I'll give you the 4 points, and then if you want to go ahead and pause and try these, and then we'll come back. But -1, 1, 0, 2, -5/3, 0, and 1, 4, right? And so here we have 4 points, and we want to check to see if they are solutions to this equation. So what we would do to check the first one, if we say pick -1, which is our x value, if we take that -1 and substitute it for x, we get y equals 3 times -1 plus 5 divided by 2. And that's the same as -3 plus 5, which is 2/2, which is 1. And so when we plugged in -1 for x, that told us that y was 1, which is what we wanted. So yes, that point is a solution. And then how about 0, 2? Well, y equals 3 times 0 plus 5 divided by 2. We get nope, just kidding. 3 times 0 is 0, plus 5 is 5 divided by 2. That's 2.5. Well, this has 2. So 0, 2 is not a solution to that equation. How about negative 5/3 and 0? Well, y equals 3 times negative 5/3 plus 5 divided by 2. Well, 3 times 3 is 1. So we have negative 5 plus 5 over 2. So negative 5 plus 5 is 0 over 2, which is 0. 0 is what this wanted us to check, so it is a solution. Right, so generally to check if a point is a solution to an equation, you plug in the x-coordinate for x and the y-coordinate for y, see if it gets a something true equals something true, which I'll do in the next one, or if you pick one, in this case we've substituted our x, and then we check to see that we get the y we wanted. So to show you that second way, so is it true that 4 equals 3 times 1 plus 5 over 2? So that's an unsure statement. Well, 3 times 1 is 3, plus 5 is 8 over 2, which equals 4. And since it does, yes, it is a solution. So whatever your equation is, you substitute one or both values in for your variables, and then you see what happens from there. But now I said a graph, our definition here at the top, is if we graph all of these solutions. And so let's go ahead and start. And let me write that equation again. So I had the equation y, or I'll write it in both forms, 2y equals 3x plus 5. And we knew that 3 of its solutions were negative 1, 1. 0, 2 was not, but negative 5/3, 0 was, and 1, 4 was. And so I can go ahead and plot those 3 points over here on my graph. So I have negative 1, 1, and then I have negative 5/3, negative 5/3, so that's 1 and 2/3, negative 1 and 2/3, 0. And then 1, 2, 3, 4. And it turns out that if we don't have more points, we can always generate more. So suppose I want to know what its value is at x equals 0. So when x equals 0, we get 2y equals 3 times 0 plus 5. So 2y equals 5. And therefore, y equals 5 halves, or 2.5. So we have 2, 0, 2.5. So 0, 1, 2, and a half. And we could keep doing that, and then what turns out what will happen is we would end up getting all of the values along this line. Assuming I drew it correctly, that means that our point negative 1, negative 2, negative 3, negative 4 should be around negative 3. So negative 4. So we have 2y equals 3 times negative 4 plus 5. 3 times negative 4 is negative 12 plus 5, negative 7. And then so that means y equals negative 7 halves, or 3.5, negative 3.5. So it looks like 1, 2, 3, 4, 1, 2, 3. I did a pretty good job of drawing that, right? Negative 3.5. So perfect. So this is exactly how we'll go ahead and generate all of the points of our equation. So for our first example, let's look at the equation y equals x minus 1. And generally speaking, I'm going to say, let's go ahead and start with a table. So when we draw our table, let's go ahead and in the first column, we'll put our x values and we'll put our y values. And I would say, generally speaking, we probably, if we plot the points around 0, 1, and 2, and 0, -1, and -2, that's probably enough to get an idea of what it looks like. So we'll check each of those values, -2, -1, 0, 1, and 2. And so this says y is always x minus 1. So if x is -2, minus 1 is -3. -1 minus 1 is -2. 0 minus 1 is -1. 1 minus 1 is 0. And 2 minus 1 is 1. And so now I have 5 ordered pairs, -2, -3, -1, -2, 0, -1, 1, 0, and 2, 1. And we can plot those 5 points over here. Right? Remember, this is our x, and this is our y. So to plot those 5 ordered pairs, we have -2, -3, -1, -2, 0, -1, 1, 0, and 2, 1. And we can go ahead and connect all of those points. And we get something like that. You're like, again, well, how do I know that this half is really there? That this x equals a half? Well, minus a half minus 1 is -1/2. And I would say that looks pretty believable. And so it's not necessary that you calculate the value for every single point on a graph. Because at some point we'll eventually talk about something called continuous functions. And we'll see that generally if you have enough of these points, you can go work off the assumption that, those points in between are going to be there. And so all of the ones we're going to look at today are going to be continuous functions. You don't have to worry about any jumps, any gaps, any places where they don't exist. So we'll just go ahead and be able to follow that process. Now we look at, say, another example, y equals 1/2. Go ahead, x and y, and I'll just stick with my old trusty -2, -1, 0, 1, and 2. And we always have our value. So you can have -2, have -1, half of 0, half of 1, and half of 2. And we can go ahead and plot those. Our origin, 0, 0, is a point. 1, a half. 2, 1. -1, -1/2. -2, -1. We end up with something like that. And so that line is the graph of y equals 1/2 x. I lost that x. Sorry about that. Y equals 1/2 x. And so we have 3 of these that we've graphed that kind of look like these straight lines. And it's like, well, will they always be straight lines? No, and the next 2 aren't going to be straight lines. But I do want to give you a special name. So these points, like these 2 here, are called intercepts. So the point where our graph, intercepts are points where the graph and the axes intersect. So we could say that this point, 0, -1, and what was the other one? 1, 0, 0, -1, and 1, 0 are intercepts. And something else that is important to know is we can specify x-intercepts and y-intercepts. And so this one on the left is called a y-intercept because it's where this graph hits the y-axis. And this one is called the x-intercept, because that's the point where our graph intersects with the x-axis. And so similarly here, we have a single intercept, and 0, 0 is both the x and y-intercept, because it's the only point where that entire line hits either axis. Now let's see another example. Y is the absolute value of x plus 1. So remember, our absolute value function always returns the positive value of a number. Or in other words, it always returns the distance of a number from 0 on the number line. And so just like we had our distance formula for points in the plane, when we're looking at a number line, our absolute value function really is our distance formula for the number line. And so I'll go to my usual -2, -1, 0, 1, and 2. The absolute value of -2 is 2, plus 1 is 3. The absolute value of -1 is 1, plus 1 is 2. The absolute value of 0 is 0, plus 1 is 1. The absolute value of 1 plus 1 is 2, and the absolute value of 2 is 2 plus 1 is 3. And so notice here now that we have our points -2, 3, -1, 2, 0, 1, 1, 2, and 2, 3. So we have -2, 1, 2, 3, -1, 2, 0, 1, 1, 2, and 2, 3. And if we would keep going, we would see that this pattern would continue that away, and that pattern would continue that away, and we get what looks like this V. And so that's how we would graph our absolute value. Again, it has an intercept here. It has a y-intercept here, and there's no x-intercept. So a graph can have an x-intercept, a y-intercept, both, or we might be able to see an example of one with neither. We won't see one with neither today, but I promise you that they do exist. And so I'll draw one more related example here. We have y equals x squared minus 4. And I'm going to work, you know exactly what points I'm going to pick. -2, -1, 0, 1, and 2. And then y, it's going to be square it and subtract 4. So 2 squared is 4, minus 4 is 0. -1 squared is 1 minus 4 is -3. 0 squared minus 4 is -4. 1 squared is 1 minus 4 is -3. And 2 squared minus 4 is 0. And so we have -2, 0, -1, -3, 0, -4, 1, -3, and 2, 0. And notice in our last couple examples, we had these nice, like, even stair steps between each of our points, right? Where we had, like, this nice even amount between points. What we end up having here, we just made a big jump, a big jump. And I'm going to go ahead and put a -3. So here we have 9 minus 4 is 5, and positive 3, 9 minus 4 is 5. So -3, 1, 2, 3, 4, 5, over 1, 1, 2, 3, 4, 5. And we have a bigger jump there. And so now, if we want to connect those, it's going to look something like that. And I want to point something out about these last two that we've drawn. That hasn't been the case of the previous three. Do you notice something common to both of these? I mean, they both kind of have this like low point, which we'll talk about minima in a future video. But they're also both symmetric about the y-axis. So remember, our y-axis is here, so this is y. And if I were to fold this along the y-axis, both sides of that graph, or both sides of this graph, would fall on each other. And so that is one special property of some of our graphs, so functions, that we have y-axis symmetry. And eventually we're going to give a term for that. Those are called even functions, but that won't happen for a number of videos yet. I have another one that's going to have y-axis symmetry, but there's also going to be something special about it. So here I have x squared plus y squared equals 4. Now remember I said I usually like to have one of my variables alone on its side. So, and I usually like to have the y because eventually we're going to talk about functions. So these are just general equations. But for functions, we talk about a dependent and independent variable. And I pointed the opposite one. So independent and dependent variable. And usually by convention, we solve for y. And so let's go ahead and move this to the other side. We have a y squared equals 4 minus x squared. And then if I take the square root of both sides, remember we have a plus or minus square root of 4 minus x squared. And it's important to note that we can't just kind of take the square root of 4 and the square root of x squared. That's not quite how the square root works. But we'll graph our nice little table. We'll do our y. We have -2, -1, 0, 1, and 2. And then when we plug it in, we plug in -2 here. 4 minus -2 squared is 4. So 4 minus 4 is 0. Let me write this one out. We get plus or minus square root 4 minus 4. Well, that's 0. -1, we get plus or minus the square root of 4 minus 1, which is plus or minus the square root of 3. For 0, we get plus or minus the square root of 4 minus 0, which is plus or minus 2. For 1, we're going to get plus or minus the square root of 3, plus or minus the square root of 0, which is 0. And so now notice now that each of my x values has 1 or 2 y values, right? -2 is at 0. -1 is plus or minus the square root of 3, which if we put that into our handy dandy calculator, and fun fact, if you're on Android or iPhone, if you turn your calculator sideways, it'll give you their square root. 3 square root is about 1.7, so plus or minus. At -1, we go up 1.7, we go down 1.7. At 0, we have plus or minus 2. At 1, we have plus or minus 1.7. And at 2, we have 0. And so now what we have is an oval. Or I bet you, if we were a little bit more careful, we don't have an oval. We have a circle. Because from here to here is 2. And from here to here is 2. And I have a feeling that if we were able to do from here to here, which we can do, square root of 3 and 1, what's that length? Well, L squared equals 1 plus 3. L squared is 4, so L is 2. And remember, our circle has the same radius all the way around. And so while it may not look like it, this is indeed a circle. And so not only does it have y-axis symmetry, where if we fold it this way, it also has x-axis symmetry if we fold it up. So it has both x-axis and y-axis symmetry. And so what we get there is both x-axis and y-axis symmetry. And I want to look at just 2 more graphs today, whenever you're watching this video. We have the equation y equals negative x cubed. And I have x and y, negative 2, negative 1, 0, 1, 2. We're going to take the negative of its cube, so 2 times 2 is 4, times 2 is 8. But negative 2 times 2, negative 2 is positive 4, times 2 is negative 8. And we take the opposite of that, positive 8. Negative 1 cubed is negative 1. Take the opposite of that, 1. 0, 0. 1 cubed is 1. Take the opposite. 2 cubed is 8. Take the opposite. And so we have the point 0, 0, 1, negative 1, and 2, negative 8. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 1. Negative 2, 1, 2, 3, 4, 5, 6, 7, 8. And so if we connect those, we have something that looks like that. Y equals negative cubed. Graph of y equals negative x cubed. And then, what if we would just kind of move that cube? So let's look at the related y cubed equals negative x. So we'll take our x and our y, and you'll see why I'm about to pick my different values in just a moment. I'm going to pick negative 8, negative 1, 0, 1, and 8. And so when I have x equals negative 8, we get y cubed equals negative 8. So y cubed equals 8. So y equals 2. And at negative 1, y, so y cubed equals negative 1. Y cubed equals 1, so y equals 1. So we have our point negative 8, 2. Then we have our point x equals negative 1, y equals 1, 0, y cubed, so y cubed equals 0, so y equals 0. So our point 0, 0. When x equals 1, we have y cubed equals negative 1, which means that y is negative 1. So here we have 1, negative 1. And then our last one, y cubed equals 8, so y equals 2. So our last one here is 8, 2. Notice those are do you notice an interesting pattern? We had negative 8, 2 here. And we had 2, negative 8 up here. And so they kind of swapped places. We'll study more about those in a few sections, about these sorts of functions that have this sort of relationship. But to plot it now, I have to go left 8, 1, 2, 3, 4, 5, 6, 7, 8, up 2, left 1, up 1, 0, 0, right 1, down 1, and then right 8, 1, 2, 3, 4, 5, 6, 7, 8. And then where do I go? Up or down 2? We missed something, didn't we? It doesn't just equal 8, it equals -8 because we have a negative up front, which means we get a -2. And now that so notice how I kind of got stuck. Like I noticed something wasn't quite right. It's because if I had to go up to 2, I would have had this nice, neat curve here. And then all of a sudden, it would have jumped back up. And I was like, that doesn't seem quite right to me. So as you graph enough of these, you start to develop an intuition for what the shape looks like. And like I said, we're going to start to notice that whenever we have a cube, whether it's on the x or the y, right, we tend to get this like curvy shape. Or whenever we have both being squared, we end up with a circular shape. Or if one thing is squared, we get this U shape. This absolute value, we get a V shape. And if we have just an X and a Y that don't have powers, we tend to get lines. And so I don't expect you to develop that sort of association between function, or in this case equations, and their graphs just yet. But we're going to be working on building that association between certain equations have a certain kind of graph. And we'll call those graph families in a future video. But the big points for today were a graph of an equation is when we take all of its solutions, the values that make it true, and put it on our Cartesian coordinate plane. We can check if a point is a solution by substituting them in and see if we get a true statement. Otherwise, pick some values, either x or y, and calculate the corresponding value for the other variable, plot those points, and that's exactly how you graph an equation. Thanks, everyone.